This is a malonic ester. This hydrogen is very acidic right there. And then we are creating this is a carboxylic acid. The first thing is you need to figure out what alkyl halide that you need to use. So I want you to be able to recognize what is where. This carbon, that alpha carbon is that alpha carbon. And this ester being hydrolyzed, that becomes carboxylic acid. And of course, that part, that's the one that eventually go out as a carbon dioxide. That's just going to go out. So if you recognize this is an alpha carbon that's there, then what alkyl halide do we need? We need an alkyl halide in this point. So, the malonic acid synthesis is hydrogen we got to be taking out to make an enolate by using a base. Sodium methoxide, which is a pretty not strong base, but still good enough to make 100% enolate from there. So you got the enolate easily created there. The alkyl halide is an isobutyl bromide. Because of that 4 carbon chain to be added, not 5, 4, because we are making this one. So this is isobutyl bromide and attacked by the enolate, that's just nothing but SN2 reactions, right? So we put that isobutyl groups there. And all we need to do is we have to hydrolyze this ester to the carboxylic acid. Then we have to heat it up. When you heat it up, these 2 carboxylic acid is kind of rearranges, and then one side of the carboxylic acid is going to go out as carbon dioxide. So we call it decarboxylation. And then that becomes the enol, but which will totalize back to ketones. So we get the carboxylic acid in here. So that's why malonic ester using 2 carboxylic acid was hydrolyzed, but only 1 left because it goes to decarboxylation very easily if you heat it up. So if you know these things and what malonic acid does, and the same thing can happen also with decarboxylation done with the acetoacetate as well. So it's something you got to keep in mind when you're solving a problem with it. But it is sometimes you may wonder, let's say if you want to make that, and you don't want to go through so many things. So you may think that I'll just use the enolate of the acetic acid. Why not be using an enolate of acetic acid? And then that's going to attack the alkyl halide. And then we can probably make this one a lot easier, right? So why don't we do that? There's a simpler way to make it happen. Why don't we have to use a malonic ester and then do the alkylation? I mean, at least alkylation is going to be the same on both parts. But hydrolysis, decarboxylation, why do we have to do that? The reason is, if it's a carboxylic acid, like acetic acid, it doesn't make an enolate very easy. First of all, this hydrogen of an acid, this is very acidic. So that's the one that goes first. So if you treat the base, you're going to make an anion right here. That will make this anion difficult to be created. Double anion is such a small molecule, it's almost impossible to be formed unless you're using really, really strong base and just push the reaction so hard. So that's the reason. This is probably not a good way to go. If you want to use the acetic acid, not the malonic acid, then you better use at least an ester. If you have an acetate and the ester of the acetic acid, then at least you can create an enolate, but that has to be done with a strong base, right? Because of that not very acidic hydrogens. But once you got the enolate created from an ester, then you can do the alkylation, and then you got to hydrolyze this methyl ester in the end. Then you can make the same thing, a little different routes. But this one, you got to create that's going to require strong bulky base. This is really expensive. That one's a lot cheap and very easily available. And you got a good deal. So if you only make a small quantity in the laboratory, it doesn't really matter. But if you have to make it 100 grams, kilograms, 100 kilograms, then it makes a huge difference. So that's why people still doing it nowadays.